with periodic trends, first thing, we're going to just talk about some factors that affect the periodic trend. First thing is the nuclear charge. So the nuclear charge, the factor that we're looking at that affects it, how does it, basically I'm asking you, how does a nuclear charge affect the periodic trend? Well, as it goes across, what are each of these called? What are each of the vertical columns? Groups. So as we go across each group, across the periodic table, your nuclear charge increases. Right? When we look at a charge, we notice that the charge will increase as we go across the periodic table.
Wait, by the horizontal or the vertical?
We're going this way. So you're starting off at group 1 to group 18.
Okay.
So it increases as you go across a period, and basically it's the example I'm giving you is think of it as a magnet that gets stronger and stronger. More protons attract the electrons with more strength. So as you grow and grow and grow and you get more protons, that will increase the nuclear charge. All right, shielding effect. This is another factor that affects the periodic trend. So a shielding effect increases as you go down a group. So I'll put that up there now. So here's your shielding effect. It increases as you go down. So additional energy levels block the pull of the nucleus on the outermost electrons. Okay. So your atomic radius trend. So whenever, you remember back in some of your math classes, you'll see you're given a circle. When you're asked to find the length of inside the circle, what is that called? The entire circle. The diameter. So finding the diameter is one thing, but then you're asked to find half of the diameter, which is called the radius. This is exactly what we're doing here, the atomic radius trend. So this is basically saying generally defined as half of the distance between the nuclei of two of the same types of atoms. So you're finding half of the distance between two of the same types of atoms. That's just the atomic radius trend. And those increase as you go this way and then down. So you'll notice over here the smallest, and it gets largest over here. Okay?
The picture on the first one, was the arrow going this way or to the left?
Which one?
Like the nuclear charge. I think it was.
It increases as you go that way.
Okay, thank you.
So basically towards the noble gases. All right, ionization energy trend. So basically all this means is it's just the energy required to remove one electron from a neutral atom. So I'm telling you that hydrogen is neutral. Basically, it's just it really has no charge, but the energy that's required to move or to take away that electron increases as you go further up and over. Now, think about it in an aspect of like valence electrons. When we say that column number 1 has one valence electron, it's a lot easier to get rid of that one electron than it is to get rid of, let's say, how many does the noble gases have? How many valence electrons? 8. So it's a lot easier to get rid of this one than these 8. And that's why the energy increases as you go across, because more energy is required to take away all those electrons, those 8 electrons, versus if you were right here, just this one electron. Got that?
Yes.
All right, so electronegativity. We said yesterday that fluorine was the most electronegative element. Basically, all electronegativity means is it's just the ability the ability of an atom to attract an electron. So the more electronegative it is, the more it's going to want to try and accept and attract those electrons. So fluorine, being the most electronegative, right here, what's the least electronegative? Francium. Okay, so basically the trend, the electronegativity increases as you go across the periodic table. So you're going from the bottom left to the top right. So on this one, the noble gases have 0 electronegativity because they do not form bonds. Now, why won't they form a bond?
Because they have 8 atoms.
Right, they already have 8 valence electrons. Their shell is stable. They don't want to bond with anything else. They don't want to give anything away, take anything more. They're happy with just 8. That satisfies all the noble gases. They're content with what with where they're at. So they're going to sit there and they're going to take, or they're going to say, we have no electronegativity, meaning we don't need any more electrons, so we don't really have a desire to attract any. And those trends are right there. So as you go up and over. Okay. Lastly is the ionic radius trend. So we talked about the radius being half of that distance. In a cation, cations are positive, and that's because those are losing electrons. It's losing that negativity. So that's why it's going to be more positive. So an ionic radius is smaller than neutral atomic radius because the same number of protons is pulling on fewer electrons. Versus an anion, which are negative, and those become negative because those are gaining electrons. They're taking on more electrons. The ionic radius is larger than a neutral atomic radius because the same number of protons is pulling on more electrons. So think about it in a way of a rubber band. If I take a rubber band and I need to basically get the entire area of all of those electrons, I need to take that rubber band and wrap it around all the electrons. The rubber band's radius and even diameter would be smaller in a smaller element. So like if you look here, lithium, it gives you, well, lithium only has three protons and 3 electrons. So it's got those 3, but the 1 valence electron. So it's small. It doesn't need to cover that much. But then we talk about these noble gases that have more electrons. So versus lithium and a noble gas, which one is going to have that larger atomic radius? The noble gases, because they're covering way more. They're covering more of a surface area. They're covering more electrons. So by covering all of those electrons, that's why it has to have that larger atomic radius. And noble gases was kind of a bad example only because those don't have a need to gain or lose any electrons. Those are satisfied. So I can say fluorine instead, all of your halogens. Those are more likely to gain an electron because they want to be satisfied. They already have 7, they want 1 more, that's going to give them 8 and satisfy that rule. Make sense?
Yes.